takes about 30 minutes. You don't have the whole day to do this. Right, and that these challenges, you know, are always there, and you have to solve the problem in presence of those. Okay, so basically, goes on. You are giving those scans just like that. This is what comes out of the laser scanner. Actually, much worse things come out of it. These are just cleaned to make it a better visual. And so in all these things, the added component is the CAD model, right? So we always have the CAD model. That is the thing. That's the point of doing the entire thing. And you want to get to such a reconstruction, and this is just the object that you have seen before. Like, this is a complete 3D. You can store it, you can do quality inspection, you can do everything with this. And actually, this is what comes out of laser scanner, so not the previous ones. So you see, there is all the factory is behind, and the object is here. If you can see it here, it's more clear. Also here is clearer, but you always observe it just a part of the object, because in 3D occlusions are much more problematic. It's not like images. So we are dealing with 10 to 100 million 3D data points per scan, and so that's times 30. And we want an accuracy around 1 to 2 millimeters in a 10-meter range. That is super small number. And we have 125 meter cubed objects in general. So it's 5 meters tall, 5 meters, the width is 5 meters, height is 5 meters. Right, and there are no color components, so don't think of this color. Everything happens in geometry, so everything is just points in space, that's all. And the CAD models that we have deviate significantly from the reality, because whenever they are manufacturing something, of course they want to manufacture the CAD model, but they cannot do it, really. A lot of things go wrong. I mean, it's even sometimes operators forget what they are producing and just do weird stuff. So, right. So the CAD models look like this. Also, it's a problem. So they are just, you know, these models are someone sits in the computer and just designs a model without thinking of parameter. Or of course, they might think about manufacturing parameters, but they definitely don't think about computer vision parameters, like how to detect this object or how to reconstruct this object. It's not in the mind of the designer, of course. And then they generate these shapes with vertex distribution like this, or point distribution, which means that there are no points here in between those. It's just connections. It's just virtual faces that make up the model. So how can we even, you know, speak about doing a point cloud processing for this when there are no points there? Well, I can just tell you what people were doing a little bit before. So they were all the scans, match it to one another, all these scans. So you search for the best match among all these scans and try to reconstruct something that is there, and hope that this corresponds to the actual reconstruction. Of course, this is a very erroneous process. Or you would, how many of you know the Kinect camera of Microsoft? Comes with Xbox? Okay, I see a few hands. And okay, so this is basically a 3D camera, and one of the applications that it has been used in is Kinect Fusion. In that application, you would take the camera, you would slowly walk around the object, right? And each scan is basically tracked, and each scan is registered on top of each other to gradually reconstruct the object, right? And you cannot do it, obviously, in this setting, because so this is the volumetric methods. You cannot do it because first you don't have a Kinect. The laser scanner doesn't operate that fast, and you don't have all the time. And the object is just so large to walk around it anyways. Right, so we cannot do any of these. So what to do with this, right? But, you know, both of these works, they did not assume that there is a CAD model available. So we can actually make use of the CAD model for the industrial applications, right? For the real applications. So some people did it before, but they, you know, these computer vision papers, somehow they are not really good. So people took images like this, and then they know the CAD model of the car, and under the guidance of this CAD model, they wanted to reconstruct a shape from this image. Well, this somehow worked, but not accurate at all. Not at all. Yeah, there have been some other works in the similar directions. Of course, there are commercial products for this. Yes, please.
Did anyone try using echolocation?
Echolocation?
Yeah.
So we are really talking about super accuracy here. So 1 millimeter in 10 meters. I don't know an echolocation device that can do this. Do you?
Bats can do it.
Hmm?
Bats can do it.
Bats can do it?
Probably, yeah.
Sure. I agree with this argument, totally. But I don't think we are as smart as the bats as of the moment. Right, so by the way, bats use ultrasound, no? Right, so maybe it's a tough system to kind of do it with ultrasound. They know their previous location. This is not a tracking problem because you don't have a device to track. This device that you have is just a laser scanner. You put it here, you capture one shot, and then you take that scanner, go somewhere, and you take a shot there, and you don't know where you go in this process because it's totally disconnected. There is no data incoming, something like that. Right, so the conventional things, basically, what they do is they take there's a CMM machine, so you have to take the part into a machine completely, and you want to touch different parts of this machine. So just by touching, you get coordinate measurements, right? Because you know where you touch. This takes enormous amount of time because you need a probe to touch everywhere to get points, basically. There is photogrammetry. This is very nice, very accurate. So you can stick things on the surface and do some optical inspection from images. This is very nice, but this time you don't get the dense reconstruction, right? You just get some points in space, and you hope that these are sufficient to justify your measurement. And then there are some scanning techniques, as I told you. You just take a device, walk around, try to do stuff. They are also very nice. They can be very accurate, but they just don't inspect large volumes like that. So this is the problem that we. So I'll just skip some of the formulation here. So the idea here, just don't get afraid, is that you take a bunch of scans. Right, these are individual scans, and you want to put those things together into one coherent component, which is the output reconstruction, output digitization. This is what it's saying. And to kind of find this coherent component, you have to find two things. You have to find perfect rotations and perfect translations of the scenes on top of the CAD model, such that they lie in a very nice form. They form this digitized model. And this is this rotation and translation that you want to find. So maybe this is more interesting. How to do is basically the following. So the CAD model comes from the manufacturer. And then you do this preparation. You do a pre-training stage on this CAD model. So you train your CAD model such that you can do reconstruction with this. I will explain how to do it. And then, so let's cut it here. And then in the runtime, you just get these laser scans. They just, somebody gives you laser scans. And then you want to overlap those laser scans on this prepared CAD model, such that they form, all the different colors here. They basically show you one scan registered there. And they come to this, roughly they are aligned, let's say. And then, because the CAD model doesn't correspond to reality, right, as I said, you have to throw away the CAD model at some point. This guides you to do some initialization, but afterwards you have to forget about this. And this is where This is almost where we forget about it. So here we do something called a post-graph computation. This is just saying where the cameras are located with respect to one another. This information is necessary in many systems, many autonomous systems. For instance, if you are driving by a car, this is also necessary. It's the same logic. And then here we inject a lot of engineering. And out of this post-graph, so given the scans, which are aligned like this, and given a post-graph, we can run what's called a multi-view optimization, which basically refines all these scans to better align to one another, right? And that is that stage. And then you can do a lot of post-processing if you want to. Okay, so this is the whole goal. Any questions? Okay. So I just showed you these CAD models, and the approach to do this. So what we want to do in the end is the following: we want to take these bad vertex distributions, and we want to create these good vertex distributions out of it, such that we can use them afterwards. And to do that is, well, there are two approaches. I will show you the second one. So we take the CAD model, and then we render some virtual, okay, let's go like this, some virtual cameras around it. This is happening on the computer only. These are completely virtual. And these are the virtual views that are generated by each camera given the CAD model. And afterwards, you can sample this whole image domain and then kind of do a sampling of these 3D points, which are coming from the image space. So basically, this just gives you a way to sample the model nicely, just like this one. So, you know, you can generate this kind of vertex distributions on it. This is just a requirement. So, for instance, given such a CAD model or this CAD model, which is basically there are a lot of elongated triangles and structure, you can get some stuff like this. Just decent looking vertex distributions around. That's all. Yeah, like this one, or I don't know, imagine any shape. And then the second stage, we basically see the CAD model on top of the scan. So we are given one scan, and we are given a CAD model, and we want to align these things together, right? That is solving the rotation and translation problem, all in all. And for that, we can use a lot of things, right? Of course, we humans do it very easily. But doing it in the machine is slightly more complicated because you have to, you know which structure, well, you don't know which structure corresponds, right? So there are a lot of ways to parameterize these things. I will not go into the details of it unless you really want to. But what is interesting is when you want to align two shapes, you basically want to align 3 points selected from each shape. This is sufficient to align them together. Okay, so if you imagine if you have just 2 points, you know, and you have these 2 points, if you align them together, you can still rotate around these 2 points, and it will still give you the same 2 points. And therefore, this is not a complete alignment. You need the third point. So the first thing here is that there is another parameterization which is going on, but this is really not. Maybe not the most smart thing to explain here. So it's basically just saying when if you have a surface normal and then a second point, you can basically parameterize it with 2 points. That's also there is a way to alleviate this 3-point problem. So the idea is the following: we have a CAD model. Right, and let's do some feature extraction on it. This can be done in many ways, but there can be certain choices. This CAD model into a database, really like a database, nothing more. All these features extracted here. It's an inverted file, which you can feature. It gives you which points on the model can generate this feature. Right, it's a hashing basically. And then this you call the trained model, right? This is just a geometric training of the CAD model. And when the scene comes, you just do the same feature extraction. You look up your database, and then you vote for the parameters that I just mentioned above. So which points corresponds, which normals correspond. This is what you vote for. in the end. And then this gives you a detection. So the idea is to find this object within this given point cloud, and here you see it in green, if you can see it. Right, so a couple of things I can skip here maybe. Just because it might be a little overwhelming. Okay, and then, so now you have this detection, but this detection can be, there could be multiple correct detections, right? Which one is the most correct? So we have to know about this. And to know about this, basically it's called hypothesis verification. It's used in a lot of places. This is not really specific to this application. Basically, we get a hypothesis of detections, so a bunch of rotations and translations, and we want to evaluate each one of them in a good way, such that we know which one registers the best. And that is called ICP, so iterative closest point alignment. Basically, given two shapes, you just morph one to the other until the registration is perfect. And after this, you can count the number of points which are common, which are overlapping, or which are agreeing, right? And that would be a score function that you say, hey, okay, I have a good registration, right? Cool, so that's just a fast way of doing ICP, so I'm skipping also. But in the end, it comes to something like that. We have the 3D model, and we have a 3D scene. This is just the actual 3D scene. And we have these detections. They are kind of shoot out from this detector. It just said these are the detectors that are getting the high votes. So then from this is the visualization also on a 3D space. These are the same. And we go to this one single hypothesis that is here, which means that we are eliminating all the rest by this score function, which I was referring to. That's all. And we can, of course, do it in our setting too. It doesn't have to be these toy examples or toy objects. You see, this is the laser scan that we get. It's even hard to see where the object is actually, but it's kind of here. So if you zoom, you see those points which are on the surface, and this is the registration. Right. And once this is given, so once it's CAD alignment to the scene is given, you can always segment the 3D point cloud. So like this, right? You can just take out the points that are on the CAD model from the point cloud. It's just you compute the distance to the CAD model, basically. So now we are given this, given all these CAD models aligned to the scene nicely from multiple views, because we took multiple shots, and they aligned like this. You see, there is a slight discrepancy between what the object is and where we want to go. And now we have to do something to come to a better shape than this one. Right? We have to do some optimization on this. In the industrial setting, it would look like that. So, yes, and that part is kind of more tedious, but I will, yes, so I will slightly skip this. So, let me give you an overview of the timings. So, this CAD preparation is offline, right? It's a difficult algorithm to select points on the CAD model such that they are apart with certain distance and whatnot. But the object detection is super fast because we can index the object in an offline stage here. And then the verification is implemented very efficiently. This whole registration scheme that doesn't have to work on all the points. You can just subsample the points from the scene and just register those points, and that's why it's fast. And then this global registration, which goes from this one to this one, that is basically an optimization where we align all the poses of all the cameras such that all these points fit very well together. So that is the energy function, right? Said in words. And then yes, so this is the configuration. So on an i5, it's really nothing special. So once again, just to repeat this whole thing, that we are given a CAD model and an industrial object like this. And we would like to, so we detect the objects here, and then we would like to reconstruct such an object. Right? So that is another example, which is like reconstructing a turbine. It's an actual turbine here, and it looks like that. So it's really, you can see that if you zoom into the details, they are super sharp and so on. And here there's a video. Maybe you can see the whole operation here, if we can play this. Right. Can you even make it full screen or not? No. Okay. So there, can you pause? Can you pause?
Oh, yeah.
Thank you. So this is an industrial scanner produced in Siemens, just a really house-made thing. And then there are many objects here, as you see. So these things create clutter. Clutter. So we are searching for this one object here, while all these other objects are around. Because I told you that it's really, you cannot move the turbine. So you have to create a scenario in your tests where this object is in all this weird stuff. And this is the detections, so individual detections here. And here you see an incremental reconstruction. So each time we do a detection, we sample the points from the scene and paint it here, right? And you see that the very difficult poses are also being recognized, so it doesn't have to be. So that is good in many applications, right? Being able to detect a CAD model within this room, for instance, detect the chairs within the room, is a good tool to have, and we make use of this. So 12 scans, 3 minutes, and we do a global optimization. So this is the CAD model, and this is what comes out before optimization, this rough alignment, right? And then this is what happens after optimization. Some slight details are corrected, more apparent in that shape maybe you have seen, or in this one. You see, it just results in a more correct, more nicer thing. And this is it's a ventil, it's again some component of a turbine, whatever. And you can now analyze how it deviates, so maybe you can stop at this point. Just navigate to the end. No? Okay, fine. Then I skip. So it's basically, at this point, you can do some quality verification, right? You can compare with respect to the CAD model, how the that is an important tool to have. So now it's also of academic interest. I told you that this is an academic work at the same time. Well, there is Kinect, and we take the Kinect sensor and we reconstruct with this Kinect fusion these models, these things, which look like that. And then we take these models and we accept them as a CAD model and just go and scan the objects once again. And from that we see if we can actually improve what Kinect is doing. And that's also definitely the case. So you can see here that there is some surfboards here on top, but this object doesn't have them. And you can just remove them, or you can go from this to here, which you see the difference between these two shapes may be apparent here. Like it's a better reconstruction just in general. Or yeah, here for instance, some mistakes that Kinect did can be corrected, or also here, yeah, the same. And if I just paint all the objects on top of each other, it looks like this in different colors. So these different point clouds painted in different colors. And this is before global optimization. You see that there are slight misalignments here and there. And this is what happens after. You see that the colors blend much better, right? Yes, so now I like to take some questions and maybe can go to the sections where I skipped in detail. That's possible.
Okay, the next question. What if we go make a snapshot of the model, wrong model, that should be snapshot of another one? Can this thing reconstruct it, or just say that it's wrong model, why there is an error or something?
Right. So this is handled in this verification part. Basically, so first of all, it's very unlikely. In an industrial scenario, right? You have this huge object, and you have a camera, and you go near the object, and you make a mistake in taking a photo of this. It's in the industrial setting, it's super unlikely that this happens, because you want to reconstruct this thing. It's not that you want to reconstruct another part. But
what if the models were similar?
yes. So what happens is the following: when you do this verification, you take the detections, which are which can be wrong really, but you want to refine them. So you want to refine them such that it fits perfectly. And if that doesn't fit perfectly, you just say, this scan is not aligning well. So you just throw it away. And if you are going in a scene when there is no object, obviously, and you just throw it away and you say, hey, I am not able to detect here. So that you can do.
Еще вопросы?
And I'm Sergey, I just wonder, are you representing some company? Do you have some products?
Oh, yes, good question. So Siemens sold this 2 times. So first of all, it's reconstructing energy turbines. It's not that the world has a lot of energy turbine manufacturers. As far as I know, there are 3 only. One is General Electric, one is Siemens, and then there is another company which I forgot. So, Siemens sells to its own factories. So we produce this software, which you have seen a demo, and they just install to another factory, right? They have 2 engineers working on this now, and they install to 2 factories this thing. So it's used in Siemens. But there is no reason why other companies should not employ such a thing also.
I guess that's great. What about fast-growing 3D printing?
What about?
I mean, maybe have you plans to produce some end-user products like 3D scanners for...
You mean like just consumer things? So this thing, that scanner, which you have seen in this video, so Siemens wanted to manufacture this for selling out, just distributing that thing. Then they made a deal with a company called Basler. It's one of the best industrial camera manufacturers to manufacture that thing. I don't think it's an end-user thing, but it would be more widespread if that sensor was going through, because that software would be shipped by, shipped with this scanner, right? Shipped as a scanner software. But it's not like you would have at your home and reconstruct stuff. I mean, Siemens is not that company. Apple would do it, right?
What is the cost of your software?
You mean when they when they sell to different factories of Siemens, right? That's.
Let's say.
I would say it's millions. First of all, because there is nothing that they can work with, and the second thing is it's not even cost of one energy turbine that they produce. So this is just the market is so, and obviously the reason is there is no high demand. It's just a couple of companies and a couple of a couple of manufacturers. So yeah, and but what I can say is if you were to sell this in general, the software is nothing, right? You can make it cheap. But then in this case, it has to be bought a lot. It has to be purchased a lot. Or you either ship this with a camera that you sell, and you sell in quantities, in volumes. That would be possible. So then the software price would go down. But when Siemens is selling to another factory, it comes with all the engineering effort in that. So it comes with a customized scanner. So the project itself costs 2 million, including scanners and stuff. You know, something like this. So it's easily in the millions range for Siemens itself.
Еще вопросы?
But that doesn't mean that the software costs that much.
Thank you for the report. Can you please explain the Siemens requirements in a sense of accuracy? So you mentioned 2 millimeters.
One, actually.
One.
Mm-hmm.
So is there a distance involving? I mean, the scanner distance and
Right.
accuracy, yeah.
So this is in 10 meters. They never use it in 10 meters. Generally, the scanners are closer. So the laser scanner can capture better. So the laser scanner accuracy is 1 millimeter in 10 meters if you have the highest quality, which means you wait for 2 hours. Not to wait for 2 hours, they just go close by the object and capture a constrained scene with higher quality that takes about half an hour. And that results in something like 0.7 millimeters. And this added 0.3 or 0.5, whatever, is the error I make in registering these things.
Do you think it's relevant for the error of production? I mean, they are assuming to estimate the error on each stage of production, right? So machinery does the stuff, does the holes, whatever. So can they be that inaccurate? I mean, producing turbines in millimeters, so is it really the situation?
Yes, it is really the situation.
And the final result that you are showing some area which has highest error, I guess, right? So that's what's the resulting for Siemens is or not. So you are showing areas of interest where they should refine their production, right? So
yes, exactly. Mm-hmm. So you highlight the regions where there are, where there are errors. So one thing I can show you is, for instance, for this image, they were testing another software as well, and you see that there are some added markers on this object. That these markers are not there actually. And when you run this whole thing in the final reconstruction, I don't know if you can see it here, but these markers are there. You see there is this little thing, or also here. So they don't correspond, and you immediately mark them in red, saying that these don't belong to the CAD model.
And there is always a trade-off in a certain bias of the model. So shift somewhere, you can either highlight with red one part or shift it a little bit and it will be highlighted from the other side. So how do you trade off with those points, right? It's like you are fitting globally to those points fields, but somehow you can shift and it will not be there. So how do you trade off?
Yes. So that's first of all, the naive approach trades off to the mean. So it basically, if you are biased towards here and here somehow, you just land at the mean of those, so the average of those, and you make small mistakes in both. This is the naive one. Of course, for this whole thing to work, there is called this robustness. So there is a mathematical definition of robustness. And that trades off a local close-by area to further more difficult to fit areas. So if you are fitting from this part, you are more likely to snap. And if you are fitting from the other side, you are more likely to fit to that side. So in the end, I would say you shrink the whole object, you expand the whole object a little bit maybe. Or, you live with these inconsistencies in practice.
So it's like a volume expansion in all sides, whatever, and you try to...
That might happen, for instance, or shrinking the volume. Because you see it from one side and you want to have the best thing there, and then you see it on the other side, you want to have the best thing there, and when you are optimizing, you don't want to move a lot from these, because because there is a notion of robustness, that there are other things that you can fit to, which you these, you prefer local, more constrained movements of these models.
And inside the name of your report, there was a sparsity word. So sparsity is addressed to the results of laser scans, I guess, right?
Yes.
You have only parts which are sparse, not the whole construction they represent.
So mostly because you scan a part, and the parts which are frontal gets more points, and distant parts, they are sampled less by a laser scanner, because you are shooting a ray, and the distance between two rays that you shoot, they increase with distance, right? So you get less points from the parts over there, more points from the parts over here.
And the mentioned process on this idea of the points, there are infinite number of points inside the CAD model. So
CAD model is uniformly sampled, yes, all over.
And you have a limited number of points which you have done with laser. So how do you take this infinite number of points available to those?
Infinite, you said?
Well, the CAD model has infinite number of points, right?
Well, if you represent it with meshes or parametric forms, that is true. If you represent it with discretized point set, it's not true.
But how do you discretize the CAD model? Is there a certain method
Right.
that you use?
So that is that is done implicitly here. So you take the CAD model, okay? Then you synthesize a bunch of cameras around it.
Okay.
In each of these cameras, you take a photograph. And you have in this photograph, you record the point index, so the 3D point coordinates, right? This is not a usual image, but you record here only really the 3D coordinate itself. And then, as maybe I can animate once again this, and then you take your discrete samples from the image space. So image space is already discrete, right? So because you have
The model is actually the image, right?
no, it's not an image. But you take those samples. So the input is the CAD model, but you virtually position this CAD model in a, let's say, like in a game, right? And then there are cameras. You just synthesize some cameras virtually. And from each camera, using a camera model, like a pinhole model or whatnot, you just take a photograph.
That's a data set which you're obtaining to train, right?
So, not really. This is just to do this discretization of the CAD model. So, all these photographs are collected, and these photographs are composed, again, not by RGB colors or not by depth. They are really the X, Y, Z. So, instead of RGB, you have X, Y, Z value in each of these photographs. And then you basically create a grid like this, so something like this, on top of the image, and only sample these coordinates. And only if it's occupied, because you don't want to sample empty space. And then you gather these things, and then all these things coming from different projections of this CAD model are being fused in 3D space, because these were 3D samples, remember? Then they are being fused in the 3D space with some voxel grid algorithm, which is like that. Right, this is just the fusion part. So I don't know if you want me to go through here, but you basically find the camera matrix and then shoot some rays, compute the intersections of the CAD model. So you go from the image space to the CAD space, intersect these things, and sample only the points where the image rays intersect the CAD model. And then you fuse them in a subsequent stage. It was too much technicality to talk about, I think. Right. So, but there is a paper of it. If you are interested in how to do this, you can read it. Sure.
Еще вопросы?
Can you please advise, are you proposing this method as a replacement for instrumental metrological control or just like addition to it?
Are you asking a tricky question?
Sorry?
Are you asking a tricky question? Because now I feel like I am proposing it as a replacement, but then I feel like I should not say this.
What? Just
Yeah, right. So I don't know really. There are things which so depends on your maybe needs, right? So there are. Let's see that thing. So this photogrammetry, for instance, is super accurate. If you just want accuracy, but if you don't want this dense reconstruction, you know, by dense I mean that all these point clouds, points come together in one shape everywhere, regardless of where you capture it from, then this doesn't do it, of course. So this dense part is a cross, right? And it's an offline thing. It just requires something called a bundle adjustment, which is really heavy process. Of course, this I would never, so this is the most accurate, by the way. So it's always the most accurate of all. So this is always the reference that I'm comparing these methods to. And the photogrammetry is probably the next most accurate. So I cannot be as accurate as CMM. It's impossible. Well, not like this. Maybe another method. But if you can live with the accuracy of 1 millimeter in this 10 meter on this large object, then there is no reason to choose a CMM over this. So it's not a CMM, well, in that sense it's a CMM replacement. But if you want micrometer accuracy, then it's not a CMM replacement. Right? Also think about it. So when CMMs were invented, there were no multiple view geometry and there were no software solution. Basically, we lacked the algorithms. Can you? No. Can you hear me like this?
Yes.
Okay. So, because still the other one is working, so I think it's good. So when they were made, the CNN machines, there were no algorithms. So these algorithms came much after, and that's why this is like a new method, right? This is like a new technology. It's not that I invented all of it. It's just invented over 50 years or something like that. So why not use this? It's just better to do these things in software than trying to fix mechanical devices. Because the mechanical devices, they heat, they age, everything like that happens. Whereas in software, you can even compensate for the heat of the camera. Right, you can calibrate you can have a model of how the camera heats and what happens when camera heats up. And just add it on top of your bias correction. Right, so in that sense, it should be replaced at some point.
Okay.
What is your argument? How do you feel about this?
It really depends on requirements, the precision, like you said.
Mm-hmm.
In case 1 millimeter is okay, or in case like just aided method for production to control by iterations during production, it can explain.
And additionally, CMM is not a solution for this application, right? Because there is no such large CMM.
No such large, and any way to take water side.
Right. Right. So you have to live with methods on that side, whatever it is. And even that is hard because you want to stick things on that model, on that object. They do this by cranes. So the crane comes in just to stick a little marker on this object. You know, and the guy on top of the crane is sticking that thing. It's funny, really.
Okay, thank you very much.
Спасибо большое всем за вопросы.